Yeah, good afternoon, good morning to the IMA webinar medical applications. So it's not the first webinar we do on medical application. That's the first one was, I think, three years ago already. We are live actually from the European Committee meeting, which has started already in the morning. The participants are still on a factory tour, but they will come in a second. But we will start, because you're all there, we will start with the first presentation out of three. And I want to introduce to you Max Müther, Managing Director of Meotec, one of our member companies and host companies of today's meeting. And he will talk about advancing medicine through additive manufacturing of magnesium alloys. Please.
Yes. Thank you for the introduction. Yeah, my name is Max Müther. I'm with Meotec in Aachen, and we are focusing on magnesium alloys for the medical applications since a long time. And in this talk, I will focus on the additive manufacturing part of it, which is a small part of what we do here at Meotec. This slide shows us what the capabilities are, which we have here at Meotec. So on the upper side, you can see the additive manufacturing, which is including the powder production and the additive manufacturing. And apart from that, we usually start with design of implants and testing of implants and also the raw materials that we provide here. And we then go for an in-house casting. So we do our own alloying systems, which are specially made for the medical applications. Then we go into forming. So extrusion of rods, and then subtractive manufacturing, for example, to do screws or implant-like shapes. After that, we also have a big surface modification area where we can either coat or also etch materials, which is quite interesting also for the additive route. And after that, here at Meotec, we have the packaging of implants. So as you can see, we start from the design, and we have the full process chain in-house, from the alloying casting to the final implant, which is being covered within our facilities. And this is all being done under the ISO 13485 certificate, which is the medical certificate that we need to have to place implants in the market. And like I said in the beginning, one route we also follow is the powder route, which you see on the top, where we do the same procedure as we kind of do below, but focusing on the additive manufacturing. So we don't do parts which are state-of-the-art like screws, but we can do any kinds of shapes by 3D printing them. And for the 3D printing of parts from magnesium for medical applications, we have this additive manufacturing process chain. And here you can see it's basically divided into three steps, which is the first step is the additive manufacturing itself, which is laser powder bed fusion in our case. So we have the magnesium powder, we position it layer by layer, and then melt it to a part. And then as we go through the slides, you will see that we also have the electrochemical cleaning and the PO surface conversion. But first, we will focus on the LPBF process. For this LPBF process, you can see here the capabilities that we have in our additive manufacturing machinery park. This is basically next to a few other machines. The main machines are the three ones that you see here. So on the left-hand side, there's a powder atomization unit, which is making it possible for us to take our magnesium alloying systems and make our own custom alloys, which also meet the quality necessities which we have for the medical sector. And the second machine is already one of two main 3D printing machines that we have, which is a really custom machine with two lasers, where we can do really complex parts with. And on the right-hand side, we have a bigger, more productive machine, which is also more the industrial version of laser powder bed fusion. To start off, as I said, we need the powder itself, and to get the powder that we need for the additive manufacturing of medical applications, we saw the need that it's not really possible to buy powders from scratch or from the market, because regularly the suppliers don't really focus on the purities that we need. because for the medical applications, especially since magnesium is a degradable alloy, we need really high purities. And for that reason, we do the powder atomization in-house ourselves. So on the top-hand side on the sketch, you can see how the powder atomization is being done. It's basically a melt pool, and the molten material is falling on a ultrasonic generator, which is then vibrating and the parts which are the grain size that we need are being formed. And the good thing is with this machinery or the setup, we are capable of forming really round spherical particles, which is one of the main needs that have to be met for the additive manufacturing in a good quality. On the right-hand side, you can see that from this process, we usually get different grain sizes, and we try to narrow the grain size down as much as possible. So after the melting of the material and the atomization, we're also going to sieving processes to have a really narrow grain size distribution to have a good powder for our machining in the LPBF process. The next slide shows the LPBF process itself. It's quite familiar to many of you probably, but it's not too familiar for the manufacturing of magnesium, because magnesium has some specialties with it. Once it's really, really light. So the material itself, if you have a gas suction, you have to find a really narrow spot where you have enough gas suction to get rid of the vapor that you see here, but you don't want to suck away all the powder from the powder bed. So this is a really small sector that you have to work in. And as you can see, like I mentioned, the material, we need quite a lot of energy to crack the surface of the material to melt it, because it has a ceramic surface because it was oxidized. We need to crack this to melt it, but then we have a lot of energy which also partly vaporizes the material, leading to this kind of smoke you can see there. And we adjust the parameters between bulk material and also scaffold material, which is the more interesting part for us in the medical sector. And for both, we can really form fully dense materials, as you can see in the cross sections in the bigger magnification. And what you also see in the bigger magnification, there's some lighter parts, which is the outer surface of the powder particles, which is the oxide, and you can find this within the final part. And for this case, it was WE43, the alloy that we used, which is a rare earth-based alloy with yttrium phases in it. Having said that, we can match the necessities of final parts regarding the tensile testing or the tensile strength. So we can reach up to up to 300 megapascals of tensile strength, and the elongation is over 10%. And we can kind of tailor the material by doing, for example, stress relief annealing or so forth. And you can see below the resulting grain sizes that we get from the different process treatments. Then we come to the next step. So as you see on the left-hand side, the material, once we get it from the additive manufacturing process, it's quite rough on the surface. We have many sintered powder particles on the surface, and the final shape that we want isn't met already. So what we have to do is we have to do electrochemical cleaning, which is a process that we also developed in-house. And the shape that we're looking to now is a 3D complex porous structure. And now I hear myself for some reason.
I have to stop it there.
But yeah, it's a 3D complex structure, and we are able to chemically clean it inside and out. And how do we do that? We've built our own electrochemical cleaning machine. So this is an electrochemical process that was developed in our laboratory, and we can do this for titanium, different grades. We can also do it for aluminum and of course for magnesium. And we developed it especially to work on additive manufactured parts for the medical sector, to reproducible clean parts in that area. And since it's electrochemical process, many of the companies that we talk to don't have this process in-house because it's really specific and you need to know many things about chemics and also electrochemical knowledge. And we built the machine in a way that you can put it into your machinery park without having to do too much around it because it's working on its own and it doesn't need too much chemical knowledge because it comes in containers and the machine is autark itself. If we take a look at the results, as you've already seen on the bigger screen, for the magnesium part, here's a more definite view on what the difference is, because you might think that, for example, sandblasting would also be a good opportunity to do it, but there's different things that are not as good as with electrochemical cleaning. First of all, you can see the outer node of such a structure can be cleaned quite well with sandblasting, but if you go on the inside, then it's already difficult because the sandblast particles don't reach that area. And with the electrochemical process, we can reach all regions and we can take away material from all parts that we want to. And of course, we have the advantage that we don't have any material which is being implemented into the material because we don't have any particles which might go into the surface area, and we only take away material. The structures that we do and which we also looked at are mostly test specimens so far. And these tests, I mean, we are also in applications already, but in this presentation, we mostly looked at test specimen. And here are some examples of how we can tailor the properties of these test specimen. So we can do different strut and pore sizes. So we can tailor the material to the needs that we have in a medical application. For example, to force cells to grow in, and also for the strength that we want to reach. And in this case, we were able to, by this strut size, strut pore size 500 micrometers, that was able to keep over 51 megapascals, which in this case meant you can put 1 ton of weight onto this really small specimen. The last step that we do in-house, which is a big field at Meotec, is the PEO surface conversion. As you know, magnesium is a quite reactive alloy and it's degrading or corroding quite fast. And this corrosion, we want to have this degrading in the human body because that's the idea of the material. But we don't want to have it too fast. So this PEO surface conversion makes it possible for us to slow down the degradation, have a degradation protection of the material. And this is also electrochemical process. And as with the electrochemical cleaning, the process is capable of reaching all regions of the part and build up a surface conversion layer inside and out. And if we take a look at the difference between first of all, between materials that we produce in-house versus commercial available WE43, and then again, looking at the PEO surface converted materials, we see quite a huge impact. One of the tests we do in-house is degradation testing by measuring the H2 evolution. So the material is being immersed in a medium where we simulate, in this case, body fluids. And by doing that, we can see how does the material probably behave in the human body. And by collecting the amount of H2 gas, we end up seeing how fast does the material degrade compared to other materials. And looking at this small test, which was only covering, in this case, 3 days, we already see that commercial alloys, which are on the top, are corroding quite fast. And these are all 3D printed samples, by the way, bulk material. But if we take commercial powder, they corrode quite fast. If we take our WE43 Meo, because it's really, really clean, it already corrodes way slower because, for example, we don't have any iron in it. And if we then do the PEO surface conversion, you can see that it's almost not visible in the first days. So the corrosion slowed down quite a lot. And this benefits the material. We want to, of course, also in the human body to have mechanical strength because the implant has to serve some kind of a use. and this use is also mechanical. And here we did a small comparison by degrading samples with different sizes and different surface treatments in a certain amount of days. And then we took them out of the degradation setup and did some compression testing. And on the left-hand side, you can see the compressive strength, which is resulting. So on the top hand, you can see it's PEO coated with a strut size, with a cell size of 650 micrometers. The next one is also PEO coated with 800 micrometers. And below we can see uncoated samples or heat treated samples. And the graph is quite graphic, I would say, but the more interesting part is probably the right-hand side. You might see that you don't probably need to do that much compressive testing to see there's a huge impact on the coating because, of course, for example, the 21-day sample was already corroded so much that obviously it doesn't really take any force anymore. These cell structures that we produce can be done in various ways. So on the left-hand side, you can see certain examples of cell sizes that we can produce. So we can tailor the material in many, many different ways. We can do full volume, we can do lattices in all kinds of directions, and this usually leads to many different options regarding the mechanical strength, the degradation, and so forth. And one application which could be used or which is already in research is to have patient-specific implants, which for us at Meotec is the idea. So we want to take the material and replace bone where there was any kind of disease or fracture, and we want to take the 3D printed magnesium parts tailored specifically for the patient based on CT data. And on the right-hand side, you can see we are able to do various different shapes, and there can be many options where in the medical sector they could be used. Then one outlook for the end of the presentation is we not only do magnesium itself, we're also doing some research on zinc magnesium. So there's magnesium inside, but it's a zinc-based alloy. And also for this alloying class or this material class, we're successfully doing the additive manufacturing, and the density is quite high, and we have a lot of strength because the zinc is an even stronger material than the magnesium. And the last outlook that we have is we are really on the research part of this additive manufacturing of new materials, because in a project that we're doing, we're not doing magnesium or zinc, but we have a powder coating system, which is capable of having magnesium and zinc in different containers, and then partially placing the different powder particles within the powder layer. So we're kind of able to print 3D printed parts with different materials in one part. So we can tailor the material in a way that we want it to. For example, fast corroding material in one place, slower corroding in the other place, or strong at one position and a little less strong at the other. So this is something that we're working on in that field as well. And yeah, with that, I want to thank you for your attention. Thanks.
Thank you, Max. I'm not sure if we can get questions from the audience online.
Yes, they can use
Yeah.
the Q&A feature.
Yeah, we don't see it here. Can I ask a quick question?
None
Yeah,
that
yeah.
have been submitted so far.
Okay, we take questions from here.
All right. On slide 9. Yes.
The etch has received 1.1 micrometer and then etch 1.7 micrometer. What type of etching is that?
And so this was so we kind of, so the naming of it is probably a little bit confusing. As received, we have a corroded or like a passivated surface, and we took an etching process and we took away the passivation, and then the final process was the electropolishing. So basically the electropolishing is the most interesting part, where the surface is really shiny. Beforehand, the roughness even went up a little bit, but we removed the yeah, the passivated parts.
I'm just wondering why or how after etching the RA, I guess, increased in thickness.
It's not the
Am I-
thickness,
am I
it's the roughness. So the roughness
the
increases a
roughness.
little bit. Because
Ah,
the
okay,
etching
so
was
it's-
quite aggressive to take away the passivated surface, and then we had some pits, but these were removed again after the polishing.
Thank you.
Any more questions? No, do we have questions online, Andrew?
Yep, there's one that just came in, or a couple actually.
Can
Yeah.
you pick out one because we don't see them?
All right, so the first one here is, what is the relation between Meotec and medical magnesium?
All right, so Meotec and Medical Magnesium are closely collaborating, and Meotec is really focusing on the technology of the whole magnesium sector, and Medical Magnesium is focusing on implants and certifications and market entrance of the implants that Meotec produces for medical magnesium.
Okay, and the next question was, what are your thoughts on iron implant with specific coating?
To be honest, I'm not the expert. Maybe Jan can also comment on that later on, but iron is just another material that is also degrading. I think it's degrading slower, right?
Also,
A lot slower. So for the applications that we have, it's too slow for us. But there's certain applications that are being looked at, like stents, for example. I think there's some iron stents on the market, even though there's also magnesium stents. But for us, it's too slow, so we focus on magnesium mainly.
Okay, Andrew, any more?
Yep, a final question. Do you develop magnesium alloys like magnesium, Ca, Zn, and other ones?
Yes, so I think it's not in this presentation. Christoph gave a presentation beforehand where he probably showed the different alloying systems. But we have two alloying systems that we have at Meotec, which is rare earth based WE43. Then we have ZX00 Meo, and this is calcium zinc based. But those are just alloying systems that we have by us, so you can buy them off the shelf by Meotec. But if you have a certain alloying system that you need tailored to your specific needs, we are capable of doing any kind of alloy that you need. So we have our own foundry, like I showed in the beginning, and we can do kind of all alloying systems, but of course, always focusing on medical field, high cleanliness, and the medical applications.
Okay, thank you very much again. Thank you. We move on to the next in-house speaker, and maybe you can elaborate a little bit more on the relationship between Meo and medical magnesium. Say hello to Dr. Jan Martin Seitz, Vice President R&D Product Management of Medical Magnesium, and he will talk about magnesium offers outstanding properties for biodegradable implants.
Exactly. Thank you, Martin. Thank you so much. Can you just quickly help me to change? Yeah, just start the presentation. I started. Is the chair already then? Yeah. Okay, perfect. All right, so very warm welcome to the local audience and also to the online community or online audience. I guess this presentation here is going to be a very nice addition to the tour we just had in the facilities and workshops of Meotec. Before we start the presentation, sorry, online community, but I'll have to circulate some implants here. So you can get a better idea of what we are actually manufacturing out of magnesium. My presentation today will touch the very basic features and properties of magnesium to explain why this material is a very nice candidate for biodegradable applications. And I've heard this question here kind of the same way a few times when we were downstairs in the workshops. The questions were relating to degradation properties and mechanical properties mostly. And these are exactly the fields we have to touch ground with today a little bit to see why magnesium is such a good candidate for these biodegradable applications. So we'll have a look at the mechanical properties of magnesium to find out if the properties, or to see that the properties are adequate for implant applications in bone, for example. We'll also have a look at the biodegradation properties or profiles of magnesium, because this is a key property when we talk about biodegradable materials. And last but not least, as something is biodegrading in vivo, it releases byproducts, and these have to be biocompatible. So we also have to have a look at these. There's a fourth category, which is quite important. The material we are working with should be good in terms of its manufacturability. But I guess, as we have heard a lot about manufacturing of magnesium today already, we're not going to touch this topic. This is very straightforward. You all know the processes, casting, forming. It's very straightforward, as mentioned before. All right, so we start with the mechanical properties here, and I'd like to introduce you to a very standardized diagram here. You can see it in a lot of publications. This basically displays the strength properties of various medical implant materials right here. So what we see is the mechanical properties of common titanium, cobalt, chromium, and stainless steel materials, which are the base materials of permanent non-degradable implants that are used these days. We also see the ceramics, zirconia, alumina, and as a reference, the cortical bone strength properties here. And in the tiny corner, right, quite close to the properties of cortical bone, there are the properties, or there's the balloon, which stands for the mechanical properties of magnesium. There's one group missing, and we have to unfold this diagram a little for the group. It's the polymers, and they're right on the left bottom here, as their strength properties are usually weaker than those of cortical bone. And why I'm showing this, it's important for us as implant manufacturers, designers, because it basically defines the size of the implants we are manufacturing. The higher the strength properties of a material, the smaller I could potentially design an implant. So titanium implants, for example, could be a little smaller than magnesium implants in order to take the same loads. So that's why when we talk about magnesium alloys, we usually aim for high strength properties, but we always have to have in mind, as there is still a gap between the standardized permanent implant materials and magnesium, dimensioning wise, we have to develop something special for the material. As a side note, the polymers, weaker as human bone, usually has the issue of a limited applicability in loaded condition, because they are so weak. If you would, for example, use a polymer in a loaded situation in a plate shape or something, the plate would be quite thick in order to take the local loads, and that's usually not feasible. So these are limited candidates, but magnesium with its strength properties is quite a good candidate. On the next slide, we basically see the playground. We have seen there's a balloon that stands for the strength properties of magnesium, and the playground is basically defined by forming processes and alloying processes. And the impacts of these processes on magnesium, that's something I'd like to very quickly want to show to you. So as a reference, there you can see the strength property bars for just as cast magnesium. It's quite weak. I guess there are only very, very limited technical applications you could use such a material for. But what we see here, if we just use a forming process like an extrusion or rolling process, we can significantly increase the mechanical properties already. And this is due to grain refining effects mostly. An alternative would be alloying. So in this case, I'm showing the strength properties for WE43 as well in as-cast condition. And if we compare this to the as-cast magnesium, we see there's also an increase in strength, which is due to the precipitates that arise due to the alloying elements. And of course, I guess the next one, everyone already knows what's happening. We are combining both ways. We use an alloy, and we use a forming method like extrusion, and then we end up at the top of the balloon that just spun on the diagram before. Very high strength for magnesium materials here, and this is exactly where we want to end up with in the biomedical field. All right, so we just saw the initial mechanical properties. That's important when we talk about biodegradable implants, because due to the degradation, they will suffer a loss in mechanical strength over time. So that's why we have to have a look at the second category I just mentioned, the corrosion properties of magnesium. And it becomes maybe a little more scientific. So we have to look at some chemical reaction equations. And what I'm showing here is the very basic chemical reaction equation of magnesium and water. And what happens here is that some ions form, and there's also a hydrogen release. And this hydrogen release here, that can create some headaches when you develop magnesium implants, because there's always 1 liter of hydrogen released when 1 gram of magnesium degrades. And that's not something you can change. The only thing you can do is you can define the period in which the hydrogen is released over time. And this is something you really need to control. And typical mechanisms to control the release rate are finding suitable alloys, finding a suitable forming process, and last but not least, applying a coating if you want to. So in the end, what we are looking for is the search for a very nice combination of all 3 of these parameter sets here to create an adequate base material which can be used for biomedical applications. All right, we see there's a lot of happening by just this equation, and we have to go a few more steps from here, because the ions, magnesium, the hydroxide ions that are released, they usually form a magnesium oxide layer. That's what is shown in the second equation here, the magnesium hydroxide layer. And this layer looks like, as shown in the picture, it's cracky, it's not dense, and everyone here and also online can imagine that this layer is not contributing to any load-taking capacities of the base material. So as this layer arises, the implant already suffers a loss in strength. And this is exactly what is expected and what is wanted. But we have to make sure that this loss in strength does not occur too early. So in this schematics here, we basically see what is ideally wanted. We want that the implant creates an artificial support as long as the bone healing phase is active. And as soon as the bone healing is completed, the bone can take over loads again. So there's a sweet spot. And by finding the right materials, the right coatings or forming processes, you have the potential or the ability to just move the sweet spot to the desired location. However, there's more. We already touched the topic of hydrogen release. The release rate must not be too high. If the release happens very rapidly, something like shown in the image can happen. Local gas accumulations, as shown in this X-ray here. In this case, there was a too fast degrading alloy used within an animal trial, and we see these gas accumulations in the soft tissue surrounding the implant. And this is causing issues, a problem. It's a too fast degrading implant material. What is required is adaptation of the parameters used, potentially a new alloying system that is used, maybe a coating. But this is an adequate, not an adequate way to treat a patient. However, third effect that happens when magnesium degrades is a shift in pH. As magnesium degrades, the pH will rise, and a local alkalosis will be the case. Luckily, the physiological system of humans is quite effective if it comes to unwanted pH raises. There are some physiological buffers available that will immediately fight against this pH raise. So there are usually no concerns in this manner. And what's interesting is that bone healing usually relies on higher pH levels. So this is this reaction here, or partially a reaction, will potentially also support the bone healing, as osteoblast cells are motivated to build up bone again. All right, so we see there's a lot of there are a lot of products released in the environment, and we were just touching just the tip of the iceberg. But we have to have a look at two more reactions that will happen as an interaction with the physiological system. Now I'll do this on this slide here. So what we see on the left is a schematic of the initial surface of magnesium implant, which is exposed to human body fluid. And the first thing that would happen, as per the equations I was just showing, is there will be a formation of a not dense but cracky magnesium hydroxide layer right on top of the implant. So far, so good. But now there are constituents in the body fluid, and they will interact with this layer or layer structures. And there are two reactions we should shed a little bit of light on, because they have major impacts. First of all, there's a reaction of the magnesium hydroxide layer with chlorine ions. And what happens is that magnesium chloride is forming on the implant surface. But this compound is highly soluble, so it will disappear. And you can easily imagine what happens here is a destabilization of the already cracky degradation layer on top. So it's basically a degradation booster. Degradation will happen more rapidly in vivo due to the chlorine ions. And on the other hand, we see there is a very complex compound that forms on top of the implant. It's an apatite. That basically appears due to the shift of the pH. With higher pH levels, the solubility of these apatites drops, and they recrystallize on top of the implant structure. And this is kind of a counter reaction to the one reaction we were just describing, because in this case, there forms another layer on top of the implant, which will slow down the degradation. But this one has another positive impact, because this is basically the nutrient for osteoblast cells, and these are the cells that build up bone. So what we can expect here is that in the vicinity of these magnesium implants, bone growth will be just boosted by this partial reaction. All right, so what we see, a lot of magnesium is released in the human body. And now we have to talk about the third set of parameters, the biocompatibility, because whatever is released here needs to be digested in quite a well manner by the physiological system. And when we talk about magnesium, we see that just from the very basic numbers that are given in literature, that this material is quite a good candidate in case, or if it comes to biocompatibility. In every human with an average mass of 70 kilograms, there are up to 30 grams of magnesium available. They are stored mostly in bone, exactly where the implants are implanted to. And we anyways have a daily requirement of up to 500 milligrams of magnesium. Just as a reference, one of the screws in an average size has around 150 milligrams. So it wouldn't be an issue if one screw would dissolve in a day, because with that, you would just cover a third of the required amount of magnesium. Anyways, magnesium is released, and it is responsible for a lot of reactions in vivo, part of the metabolism of sugar, fat, and proteins, part of the regulation of enzymatic reactions, transport of salts, growth of bone, and it regulates the muscle and nerve cell function. However, excess magnesium is simply excreted via the kidneys and the liver, and the same currently accounts for the alloying elements that are used. All right, so we see just from the mechanical, biodegradation, biocompatibility performance characters, magnesium is really a quite good candidate for these biodegradable applications. And with such materials, it is possible to create implants that cause or lead to the avoidance of removal surgeries, as they will simply turn into bone after the job is done. That's something you can see at least partially in the histological image that is shown here, where a device is partially degraded. So the black area marks is still the metal, but you can see where there was a thread in this cross section. It's partially gone and sometimes turned into bone cells already, which is the very violet or other very violet colored sections here. And the bone seems to pretty nicely align to the surface of the implant. At Medical Magnesium, we created 3 product families based on this technology. Compression screws shown on the top left here. These are screws that are basically used to support fracture healing as they create a compression force over a fracture gap. We introduced the interference screw devices into the market, which are screws that clamp tendons and ligaments into bone, for example, in ACL and PCL repair surgeries. And we also already introduced PIP devices, which are meant to stiffen joints in fingers and toes. And all these devices have in common that they offer quite a high stability. Just for reference, the stability is 4 times higher than the stability of currently available polymers in medicine. And depending on the size, they will biodegrade in a period of up to 36 months. And all these devices, which we offer at Medical Magnesium, they rely on the combined technological approach. So they base on the alloy WE43 Meo, which is an alloy Max just recently introduced to you, that offers for our purpose high strength and homogeneous degradation performance. And we combine this with a PEO surface modification, like a ceramic top layer, which delays the initial degradation reaction. So we decrease the hydrogen release into the adjacent tissue by this surface modification here. And this way, we avoid burst degradation effects we could potentially see in the tissue. All right, and with this, I'd like to show you some of the examples, some images from our lucky customers, some X-rays, and some different application sites for our implants. So in this case, we see the application of our compression screws in a foot, and you can see the fracture line, which was right here, seems to close over time. So we can compare the 6 weeks and the 12 weeks group here. So basically the job of these implants is done here, and the degradation can just simply progress until the implant's gone and until it's being replaced by bone. See another application site here. It's within the knee, 2 screws in the patella here, and also the use of the devices in a femoral condyle with follow-ups of 2 weeks and 12 weeks in these cases. And just as a last example here, the use in the ankle. Fracture line is barely visible in the 12 weeks picture. So the screws seem also have to be done quite a good job here. And yeah, with these, I would say very positive images because the patients are happy, fractures are healed, and no second surgery is required. I'd like to close this very quick overview, and yeah, thank you very much.
We have any questions here? No, maybe they're coming. Any questions online, Andrew?
Yes, one question. What magnesium alloy do you use for your implants?
We use the WE43 system. which is basically magnesium, some minor amounts of rare earth and zirconium.
Thank
All
you.
right,
That's all.
that's all. Thank you very much
Was a
for
pleasure.
the presentation. It's all very fascinating, but we want to avoid it, of course. If we have it, we are glad that this technology exists, I think. So as third speaker of today and also last speaker in this webinar, it's an online presentation given by another member of the International Magnesium Association, the Helmholtz Centrum Hereon. And I welcome Professor Dr. Engineer Norbert Hort, head of the Department Functional Magnesium Materials, and he will talk about biodegradable mag implant materials from an engineer's perspective. So Norbert, you have to share your screen.
You might need to stop screen share on your end, Martin.
I have to start that, okay. Well, that's
I hope you can see something.
Actually, I think I
no,
can.
we just see
There we
our
go.
presentation before.
I got Norbert's up here, so he's good now.
Okay. We don't see that, but we have to do that locally, I think. Yes.
Das ist Wechsel, ne? Willst du anschauen? Den Mann hier.
Aber er hat seinen, er hält seinen Bildschirm.
Okay, das heißt, das hier kommt weg. So,
Okay,
Okay.
yeah, very good, thank you.
aber das muss so angezeigt werden, ne?
Yeah. Now, but bear with us a second.
Okay.
Okay, thank you very much. Okay, thank you.
Yeah, Martin, thank you for the introduction. And I see some slides in the background. So I'm talking about my engineer's perspective because sometimes that's interesting. Last week I attended a conference and exhibition mostly for the medical people, and yeah, that's sometimes different because as an engineer you talk to the medical people and you see it's sometimes really difficult to come to the same conclusion. However, where we are, you've seen a bit of Meotec and a bit of medical magnesium, and it's quite interesting that we are not the only ones, but what is also interesting that most of the companies on the market are from Germany, besides Dept from Finland when it comes to CE certificates. There's others on the market as well, but without certificates. So it's an active community, and most of them, they're also using WE43 to a certain extent, and only a few are with other alloys. However, there's something going on, and we need to talk about quite a lot of different things. So we have to look on biology, definitely, because it goes into the body, and we have to look for in vitro, in vivo behavior. We have to make soil tests, we have to make tests in animal, and last but not least, it goes into humans. We need to talk about properties, and properties are based on the microstructure again, generally. So it's not only the composition, it's also the process that ends up in a certain microstructure. And that's responsible for the properties with respect to mechanics, corrosion, degradation, gas development, surface coatings, and so on. That's about the different routines a bit. You heard already about castings from medical magnesium additive manufacturing and so on. So once a time I had these three circles and the implant would have been located in here, but there's something right in the end where we also need to talk about. So we select an application, and then it comes clear that we also talk about permanent or non-permanent. We have to develop the microstructure according to the application. We have to perhaps modify the processes. However, I said it once in a different context, if you can't cast it, forget it. that's still valid. You need a powder. The powder quite often is coming from a melt. And if you have intermetallics forming in the melt, blocking the gas atomization, you're out of business. And I do not know when we made that slide, we already added something on here. That's geometry. I will later come to that again. However, that's a circle. And when you have done that properly, you have an application with a profile. And when everything is right, you have an application that may go to the market because it fulfills not only a property profile, but also the profile of the application itself. Anyway, in between, you need to answer a bit these questions, and the answer might be yes, we can. And by that slogan, you may perhaps get out when we proposed that first. Yes, we can. There was some guy in the United States becoming president. He answered that yes, we can do so. And we also did that on quite a lot of different materials for a number of applications for magnesium implants. Sometimes you also have to confess it's not working. And one of the examples is that we have problems with the processing, or that the property proof is not good enough to get a proper applications. And that's another last question we do not know. And that's research, what we are doing on a daily basis. When we do not know, we have to find out if the yes, we can be the answer, or no, it doesn't work. However, we also need to talk about different things. And from my point of view, as a materials engineer, I know exactly what a dislocation is. But when I talk to a medical doctor about a dislocation, he's having a completely different understanding what a dislocation is, what a segregation is, and even the ANIMA model. A friend of mine did listen almost interesting to a presentation, and then he figured out the ANIMA model is not really the model in the computer, but something that is alive. So we have to find a dictionary. And I also found some pictures for that. So when you look for the pineapple, there's an apple in the pineapple, but the apple in reality is a completely different subject compared to the pineapple. And again, we have to find a common language, our own dictionary, who's talking to whom, and what we need to express. And that's again some kind of daily work, because if you don't do so, you are talking basically against each other, parallel to each other. You're acting in a different universe, perhaps. That's our toolbox, the periodic table of elements. But we cannot use all of them. There's a number of them where we have no information how they act together with magnesium, let's say based on phase diagrams. Phase diagrams give you first information about the constituents you have in your alloy. And this gives you a first impression about the property you can reach. But you see there's a number of elements which you can't use in any case, and you do not have any information about. And then we are back in research. There's a number of elements which are practically irrelevant, radioactive, critical but feasible. And some of them, they're also not feasible because you can't use them in any kind of application. They have impact on the processing and all. So that's the toolbox that is left. And before I just saw a small question in the questions and answers. So whereas elements are sometimes used to fight cancer, and from an engineering point of view, I would say that's okay. They do not cause cancer. At least I do not know any publication that is telling that. However, here you have elements. You can look on the binary combination, on the ternary, quaternary, how complex they ever may be. You have a universe full of different combinations where you select elements for the processing and for the purpose that they have to fulfill within the application and while they are in use in the body. We have hundreds, thousands, I don't know, of possible combinations of processes. We can cast, in most cases we do cast, but we have a billet which can be perhaps extruded. We can make wires, we can go additive manufacturing route, perhaps by sintering, whatever. So again, we have combinations. In the end, it depends on what you need in the property profile and perhaps what you can spend in money for that. And last but not least, you need to analyze that. Right in the early stage, you have to make a composition that you designed before, and this is also something that needs to be in the final product. And here we need to talk again, because that's a spectrum that you get from XRF. And you see that perhaps some of the elements, especially rare earth elements, are hardly to detect, and they may interfere with other results. So manganese is a good example that may give you an information perhaps about the gadolinium, which is not existed in your composition. So be really careful with that. And what is also standard knowledge is when you do ICP OES, a standard procedure, you can analyze properly, but I saw the analysis made on here for magnesium 10 gadolinium, for magnesium 5 gadolinium. I was really astonished about the copper contents, about the lanthanum, because there's no lanthanum in, and about the high lead content in the magnesium 5 gadolinium compared to the low lead content in the magnesium 10 gadolinium. And we made these alloys almost the same time. The same alloys, same procedure, and this is a result that came out. A large amount of selenium. I asked a good friend, Carl, professor in analytical chemistry, and when I asked the question where the selenium can come from in the ICP MS, she simply started to laugh. That's a well-known artifact, because due to the plasma that you use to make the analysis, 2 argon atoms team up, forming argon dimer. That's not stable, but that's having exactly the same mass like the selenium. So be really careful when you get a result and you do not know about the black box that you have been dealing before. So be skeptic. Sometimes you have to bend your specimen. You have to have something like a wire, a Kirschner wire, or a cannula, or whatever. And now we are coming into civil engineering. I am a materials guy. I studied material sciences, but I also had to take courses on civil engineering, and I didn't like it. However, we have been discussing what perhaps may have an impact, and that's Young's modulus. We have iron compared to magnesium, and you see by the same weight, steel is bending drastically. By the same stiffness, magnesium is having extreme low weight. We need to consider that, but when I look to the past 20 years of magnesium applications as an implant, nobody's really thinking about it. When we look for the casting process, sometimes it might be of interest to look to an ancient book, perhaps. This is from the German Democratic Republic. Mr. Schichtel, he brought this magnesium pocketbook out in 1954, and we found a process that is called Typenguss. I don't know an English word for that, so I created that on my own, called it permanent mold direct gel casting. That's more or less the same process that was called direct gel casting before, and it's pretty interesting because you have some first, where you put in the specimen, you hold it for some time, then you dip it down in the water bath. And that's our daily work for that. On the left-hand side, you see how my colleague is adding the alloying elements. The left in the middle, he's stirring that, then we are casting that, and the good message, yeah, quite often magnesium is told to be highly flammable, but you see, no flames at all. So the cover gas is doing what is necessary. And on the right-hand side, You see the mold is getting dipped into the water bath, cooling down completely. And the advantage of that process is pretty simple. On the right-hand side, you see a standard billet simply cooled in the mold by air. You see drastic shrinkage. You see large elongated grains, and this you can completely avoid by this kind of process. So select your processes accordingly. And with this process, you have almost no porosity. It's homogeneous from a chemical point of view. It's almost homogeneous with the grain size and the orientation of the grains. However, again, there's a detail that you have to look up. When you change the mold material, it may come out completely different. If you change the cooling rate, it may come not completely different. So take care of the process. Properties. When we started with magnesium gadolinium, this publication is from 2009. We saw the content of gadolinium is responsible for different corrosion rates. And again, this is based on intermetallics. So for the magnesium 10 gadolinium, it seems that we found the lowest immersion, the lowest corrosion rates with testing them by immersed and audiometer as hydrogen generation. So we can select composition with respect, again, what we need for the application. And the same is when you take tensile testing as an example. Again, you can work on the property profile simply by working on the composition and, in this case, on the T4 treatments. If you want to have a high corrosion rate, okay, make it accordingly. And if you need a low corrosion rate, okay, follow the procedure right away with the composition and the processing. And when processing, this was also emphasized before a bit, look on the processes. When you look for cast materials, the stress will not be as high as you can get from an extruded material in this case. As an example for magnesium 10 gadolinium. So it's about composition and processing, and basically that's the microstructure. With MECO, we developed a new material that we call Resoloi. We have a pattern on that. We selected the alloy elements accordingly. We optimized our ingot melting, the extrusion. In this case, we did drill also the rods. We had tubes, and the tubes are laser cut. And what is also the question when we started the discussion more than 15 years ago, we found that we don't need 640 megapascals. We don't need 500 megapascals tensile strength, and we don't need an elongation to fracture. Basically, these values were derived from steel, but finally we found out that something in the area of 300 megapascals tensile strength is okay. Then a bit more than 20% elongation to fracture is also okay. So it's not steel, it's not the apple, it's a pineapple. So it's a specific material with specific properties, and you have to look for your application. And you can't compare directly titanium with magnesium, titanium with steel, or steel with magnesium. Of course you can, but it's useless. That it's useful, you can see by the stand. I've seen that in the audience, there are at least 2 people from MECO. Contact them if you want to have the Resoloi for your materials. It's quite a nice material. Civil engineering. As I said before, I do not like it. However, I own these books because one I had as a student already, and the other I just thought I need to have it simply to compare it. They are quite nice. They are quite heavy as a brick and as big as a brick. And you also can use that English book. So these are the basics for civil engineering. And when you look for the deflection, that's also easy. You find this equation, you can calculate it. However, if you look on the maximum displacement of this cantilever, you find only one material parameter, and that's Young's modulus, and the rest is geometry. So look on the geometry. And when then you look on the bending, and you have to look for moments of inertia. That's also described in these books. Simple equations. And again, it's about geometry. And then you see there's a simple fact. You have more than 200 gigapascal for the iron Young's modulus. You define that's deflection factor 1. And you see that's 45 gigapascal. 1/5 of the Young's modulus you have for the iron, and you have 5 times the deflection. And now again, it becomes interesting, because when you convert that to a new orientation, you simply move it by 90 degrees, you still have the same relation, 5 times the reflection of iron. When you compare this geometry with this geometry, the cross-section area is identical, but the deflection is minimal compared to this one. So it's about geometry. It's not about the material's properties, tensile strength, corrosion, whatever. And you can perhaps simply answer a question: can I do it with magnesium? If yes, do I have the right geometry? If you don't have, use something else. So when we look, we already said more than 15 years ago, geometry is important, but we look mostly in all the publications, like almost any other, what is the Young's modulus, what is strength, what is ductility, what is the degradation rate, how is the biology acting. So to conclude that, yes, we have stiffness, in this case, plastic properties, but it's not related to the material itself, it's related to the geometry. Can the stiffness, in this case, Young's modulus, be tailored? Yes, of course. By the amount of solid atoms, by intermetallic phases, you can make MMCs, something else, but it has consequences. You have to look for the volume, you have to look for the geometry, and then it infects and influences mechanical, physical properties, and especially when you have an MMC, or you consider intermetallic phase something like an MMC, now you have to look again on the material interactions with biology. And last but not least, it costs money. If you're willing to take the costs, okay, that's fine. If you don't want to pay it, okay, take something else. And that's basically what I wanted to tell.
Thank you, Norbert. Are there any questions here? Any questions online?
No questions on the online Q&A.
No questions online. Okay. Thank you. I think we had some issues with the sharing, but we saw everything. So I hope every participant online saw also at least partly the slides. Will anyway, you will get the notice, and the slides will be online on the IMA website, and the recording will be also shared with the participants. So with that, thank you very much for listening in. We end here a day of intensive education and on the use of magnesium in medical applications. And for the online participants, thank you very much. Get in touch with the IMA if you want to engage with us, either via the website or directly by email. So thanks again for dialing in. Bye-bye.